I am Dr. Mukesh Kumar, Professor in Department of Mathematics. Dr. Anand Chauhan has already taught you the concepts of random variable and distribution functions of one variable. So today I am going to explain the multiple variables distributions. So in the multiple variable distribution, I will explain two-dimensional random variables, joint probability function, marginal probability function, conditional probability, expectation, and covariance. So in the first, the multiple random variables. So random variables categorized in two category. One is the discrete random variable and second is the continuous random variable. And discrete and continuous random variable connect with the joint probability function, and joint discrete and continuous random variable also connect the marginal probability function. So in the first, in a random variable, that is two dimensional random variables, let x and y be two dimensional random variables defined on the sample space S. The value of x comma y at w is given by the pair of real numbers xw comma yw, where w belongs to sample space S. The notation x less than or equal to a, y less than or equal to b denote the event of all element w belongs to the sample space S, and the probability of that event will be denoted by probability of x less than or equal to a, comma y less than or equal to b. So in that case, let us consider two events. A is equal to when the random variable x is greater than or equal to small a but less than or equal to small b, and the event b is equal to when the random variable y greater than or equal to c and less than or equal to d. That is, here a, b, c, d are the constants, that is which belongs to set of the real numbers. Then the event a intersection b is equal to x greater than or equal to a less than or equal to b intersection of y greater than or equal to c less than or equal to d. So probability of when x laying between a and b, y laying between c and d is equal to probability of when x laying between a and b intersection of when y laying between c and d. So here I am taking the definition. Here the function f dot comma dot defined by f of xy is equal to probability of random variable x which is less than or equal to small x comma random variable y which is less than or equal to small y. So in that case, here small x and small y belongs to set of the real number, that is xy belongs to set of the real number. Here R2 denote the dimension, so x comma y means two dimensional real number, is known as the df. Df means distribution functions of the random variables x and y. So here we have the two conditions. First condition is here capital F x comma y is non-decreasing and continuous from the right with respect to each coordinate, and second condition, limit x goes to plus infinity, y goes to plus infinity, f of xy is equal to f plus infinity comma plus infinity is equal to 1. Limit y goes to minus infinity, f of xy is equal to 0 for all x, and limit x goes to minus infinity, f of xy is equal to 0 for every y. So here condition 1 and condition 2 are not the sufficient condition to make any function f a distribution function. Now next, the joint probability function. So here let capital X and capital Y are random variables. Here xi means I stands for the 1 2 3 up to n and j stands for the 1 2 3 up to m, that is I is equal to 1 2 3 up to n and j is equal to 1 2 3 up to n, then the joint probability function is denoted and defined as p of x comma y is equal to f in suffix xy in bracket is small x comma y, or f xy is equal to xi comma y, and that is here I denote the dimension, that is n dimensional. This is the n dimensional random variable, and this is the m dimensional, that is I is equal to 1 to n and j is equal to 1 to m. So f x x I comma y I is equal to probability of x is equal to xi and y is equal to yj is equal to probability of x is equal to xi intersection y is equal to yi. So here p of x comma y is called the joint probability function. So joint probability function having the some conditions here, the joint probability mass function of the discrete random variables x and y denoted by this one, and this probability mass function satisfy the three conditions. First condition, f x x always greater than or equal to 0. Second condition, summation double summation xy on the xy, f of xy in bracket x comma y is equal to 1, and third condition, f xy is equal to probability of x is equal to x comma y is equal to y. So this is the joint probability mass function for the two random variables, and if these three conditions are satisfied, then the function is said to be probability mass function for two random variables. Now next part is marginal probability function. Here if we consider x in bracket xi and y in bracket yj are random variables, here I varies 1 to n and j varies 1 to m. So the marginal probability function of the random variable x is denoted and defined as px xi is equal to px is equal to xi, and is also defined as p, because here I is equal to 1 to n, so p x is equal to xi is intersection of y is equal to y1 plus p x is equal to xi intersection y is equal to y2 plus p x is equal to xi intersection y is equal to y3 plus up to plus p x is equal to xi intersection y is equal to ym, or p x xi is equal to, because this expression is denoted by pi1, this expression is denoted by pi2, this will be pi3 and so on, this is pim, that is uh, small pi's are the probabilities. So in that case we write these probability, that is sum of pi1 plus pi2 plus pi3 plus up to plus pim is equal to summation j is equal to 1 to m pij, and this summation is denoted by pi dot. So p x xi or pi is called the marginal probability function of random variable x. So this is the of the notation and definition of the marginal probability function of x. So similarly we define the marginal probability function of random variable y. So here the marginal probability function of random variable y is denoted is p y yj is equal to p y is equal to yj, and is defined as p x is equal to x1 intersection p y is equal to yj plus p x is equal to x2 intersection y is equal to yj plus p x is equal to x3 intersection y is equal to yj plus up to plus p x is equal to xn intersection y is equal to yj, or we define the marginal probability function of y in the form of py of yj is equal to, that is this expression is denoted by p1j, this expression is denoted by p2j, this expression is denoted by p3j, and this expression is denoted by pnj, and in the summation form I is equal to 1 to n pij, and this summation is denoted by p dot j. So here Pyyj or P dot j is called the marginal probability function of random variable y. So this is the definition of the marginal probability function of random variables x and y. So here marginal probability distribution MPD, if we are given a joint probability distributions for two random variables x and y, we can obtain the individual probability distributions for x or the for random variable y, and these are called the marginal probability distributions. So here I am taking an example and explain the concept of the theory. So here continuing plastic covers for CDs, find the probability that a CD cover has length 129 mm, that is random variable x is equal to 129, and given the table as the length x and the width y. So length x is 129, 130, 131, and width is 15, 16. So when width is 15 and length is 129, so probability is 0.12. Similarly, length is 132 and width 15, probability is 0.43. Length is 131, width is 15, then probability of 0.06. Similarly, for the length is 129, 130, 131, and width is 16, then probabilities are these. Then the probability of random variable x is equal to 29, which is given the x is equal to 29. So in that case, this is equal to probability of x is equal to 29 and y is equal to 15, plus probability of x is equal to 29 and y is equal to 16, and this will be probability of x is equal to 29 and y is equal to 15 means this one, this is 0.12, and probability of x is equal to 29 and y is equal to 16 means this one, this is 0.08. When we add both, so we obtain 0.20. So this is the probability when the random variable x is equal to 29. So question is, what is the probability distribution for the random variable x? So in that case, when we compute the probability distributions for the random variable x, so this is the given length x and width y. So length x is 129, 130, 131, and width is 15, 16. So here when we compute the probability distributions for the random variable x, so in that case we compute the column totals, that is these are the rows, this is first row, this is second row, and this is the first column, this is the second column, and this is the third column. So we compute the column sum. So column sums 0.12 plus 0.08 is 0.20. Similarly here 0.42, 0.28 is 0.70. Here 0.06, 0.04, this is 0.10. So probability distributions for the random variable x appears in the column totals. In that case, this one, this is the random variable, that is length x is 129, 130, 131, and the and the distributions functions of the random variables x on x, that is this x1, this x1. So this is 0.20, 0.70, 0.10, that is the column totals. In that case, when we compute the distribution probability distributions for the random variable y, so we find the row totals. So in the row totals means this one, this 0.12, 0.42, 0.06, then the sum of these elements in the, that is in the first row is 0.60, and in the second row 0.08, 0.28, 0.04, then this will be 0.40. So the uh, distribution function for the random variable is y is the width is 15 16, and distributions function for the random variable y is this one, that is 0.60 and 0.40, that is this will be row sum. This is row sum or row total. So this is the first row and this is the second row. So sum of these three elements we obtain 0.60, and sum of these three elements we obtain 0.40. So this is the uh, distributions functions for random variables x and y. Now next is uh, the probability mass function, that is PMF, for the random variables x and y appears in the margins of the table. That is, when we compute the probability functions for the random variable x and y, so when we obtain the probability function for random variable x, so we obtain the column total, and when we obtain the probability function for the random variable y, then we obtain the row total. So column and row totals, they are often referred to as the marginal distributions for the random variables x and y. When there are two random variables of concern, we also used the term bivariate uh, probability distributions or simply bivariate distributions to refer to the joint distributions. That is, when two or more than two random variables are involved, then such type of problem is known as the uh, variable multiple random variables problem. So here I am taking a question related to distribution function. So here question number 1, let f be a function of two random variables defined by capital F of x y is equal to 0 when x less than 0 or x plus y is less than 1 or y less than 0, 1 otherwise. So then f satisfy both the first and second conditions above, means this one, this is the first condition and this is the second condition. That is our aim, to satisfy both the conditions. That is, then f satisfy both the condition above. In that case, this function satisfy the above condition. However, f is not a distribution function. So in that case, in figure 1, so this is figure 1, and here this is x and this is y, because f of xy is equal to 1. It means we have a condition x plus y is equal, x plus y is less than 1. So with the help of the given condition, we draw this graph, or this graph already given in the problem. So f is not our aim to uh, find out f is not a distribution function, because this function already satisfy the uh, condition 1 and condition 2 given here. So in that case, when f satisfy both the conditions, so we obtain the function f is a distribution function or not. So in that case, this is the function, and using the concept, this concept, when x less than equal to x2 and x1 less than less than x2 and y1 less than y2, then f probability of when this random variable x greater than x1 but less than or equal to x2, and random variable y greater than y1 but less than or equal to y2, is equal to probability of random variable x is less than x2 comma random variable y is less than or equal to y2, plus probability of x less than or equal to x1 and y less than or equal to y1, minus probability of random variable x less than or equal to x1, y less than or equal to y2, minus probability of capital X less than or equal to x2 and y less than or equal to y1. Then this expression is denoted by f of x2 comma y2, that is this one, and this expression is denoted by f of x1 comma y1, that is on both variables, and this term is denoted by minus of f x1 comma y2, and the last expression is denoted by f of x2 comma y1, which is greater than or equal to 0. That is, if this condition is satisfied, then function f is a distribution function. So here we compute probability of this one, that is when random variable x greater than 1 upon 3 but less than or equal to 1, random variable y greater than 1 upon 3 but random variable y less than or equal to 1. So this expression is equal to f of 1 comma 1 plus f of 1 upon 3 comma 1 upon 3 minus f of 1 comma 1 upon 3 minus f of 1 upon 3 comma 1. So this value f of 1 comma 1 according to this condition is 1, f of 1 upon 3 comma 1 upon 3 is 0, f of 1 comma 1 upon 3 is minus 1, that is 1, and this is symbol minus 1, so this is minus 1, and f of 1 upon 3 comma 1 is 1, so this is 1. So here this minus 1 and this plus 1 is cancelled, so this is equal to minus 1, that is minus 1 is not greater than or equal to 0. If this is not greater than or equal to 0, then the function f is not a distribution function. Now the another question based on the distribution function is here, a die is rolled and a coin is tossed independently. Let x be the value on the die, and capital Y is equal to 0 if a tail turns up, and capital Y is equal to 1 if head turns up. Then sample space S, that is this denoted by A, or sample space denoted by capital S. So here the S is equal to 1 comma 0, 2 comma 0, 3 comma 0, 4 comma 0, 5 comma 0 up to 6 comma 0 comma 1 comma 1, 2 comma 1, 3 comma 1, 4 comma 1, 5 comma 1, 6 comma 1. So this is the sample space, and probability Pij is equal to 1 upon 12 when I is equal to 1 to 6 and j is equal to 0 and 1. When j is equal to 0 and I is equal to 1 to 6 is 1 upon 12. When j is equal to 1 and I is equal to 1 to 6, then Pij is equal to 1 upon 12. Then the distribution function of the random variables x and y is given by this one. Means when we compute the distribution function for the random variables x and y, so here f of xy is 0. Why? Because here x less than 1 but y greater than minus infinity less than infinity, and x greater than minus infinity less than infinity, and y is negative. So in that case this value is equal to 0. Now here x greater than 1 but less than 2, y greater than 0 but less than 1. So in that case probability is 1 upon 12, because when we rolled a die and tossed a coin, so in that case total sample points is 12, because this is given Pij is equal to 1 upon 12. And in the third case, when x greater than 2 but less than 3 and y greater than or equal to 0 and less than 1, x greater than or equal to 1 less than 2 and y greater than or equal to 1, so in that case this is 2 upon 6, 2 upon 12, so this is 1 upon 6. In this case 3 upon 12, so this is 1 upon 4. Here 4 upon 12, this is 1 upon 3. Here 5 upon 12 is 5 upon 12. Here 6 upon 12 is 1 upon 2, And in that case because y is greater than or equal to 1 and x greater than or equal to 4 less than 5, so this will be 4 upon 6. So in that case this is 2 upon 3, and here 5 upon 6, and here 6 upon 6, so this is equal to 1. So this is the distribution function f of xy for the random variables x and y when a die is rolled and coin is tossed independently. So this is the solution of both the example. So thank you very much.